Hey everyone, in this video I'm going to continue our review of linear regression from a frequentist perspective, and particularly we're going to talk about some of the properties of OLS with non-stochastic access. And we mentioned this assumption of non-stochastic access in 701 last semester when we derived unbiasedness. The property of OLS being unbiased, okay? So correct on average, you could think of. This idea of non-stochastic axes, what is meant by that is we're basically assuming that the axes are fixed. They're not part of the sampling distribution. The axes stay fixed. Everything else we can kind of resample, but the axes themselves, they're constant. Okay, and we will in a second also talk about kind of relaxing that assumption. Okay, so as I mentioned last semester, we showed that OLS the OLS coefficients are unbiased based on the following assumptions. Okay, we had the basic linear model in the population. Yn is equal to beta prime xn plus epsilon n. We had this assumption that the x's are fixed, so they're not random variables. We had this assumption that x prime x or xn, the sum of xn prime has full rank, so there is no perfect collinearity, and the assumption that the expectation of the error term is equal to 0, right? And so based on those assumptions, we can show that the OLS coefficients, the expectation of the OLS coefficient is equal to, or the expectation of our sample OLS estimate is equal to the population OLS coefficient, so to speak, right? So in expectation over repeated samples, the sample OLS coefficient is equal to the true population parameter, which is our quantity of interest, right? So that's, you know, unbiasedness, and that's already a very nice property for an estimator to have, right? Based on this kind of set of assumptions, we can add some additional, we can derive some additional properties by adding additional assumptions, particularly about this error term, right? If we assume, in addition, that the variance of epsilon is constant and is equal to sigma square, so this is this homoscedasticity assumption. So we have constant error variances across across observations, across observations, and for A6 that the error terms are independent, so they're not correlated between different observations, and A7 and as an additional assumption that the error terms are normally distributed. If we kind of add those assumptions, we can not only show that OLS is unbiased, but we can also kind of directly derive a test statistic for the OLS coefficients, right? So basically, adding those assumptions allows us to derive the sampling distribution of our beta hat. Okay, and based on the sampling distribution, following the same arguments regarding sampling distributions and hypothesis testing, we can then derive a test statistic for any beta coefficient to, for example, test whether beta, a specific, you know, regression coefficient, is likely to be equal to 0 or not. Okay, so under these assumptions, A1 through A7, we can basically show that beta hat, the vector of beta hat, follows a normal distribution with mean beta, that's kind of the unbiased part, right? In expectation, beta hat is equal to the true population beta, with a given variance. And that variance here, we'll talk about in a little bit more detail later on, is given by the variance of the error term times x prime x inverse, okay? Now that we're able to kind of derive the sampling distribution of beta hat, we can derive a test statistic to, for example, test any hypothesis test of beta hat being of some value. Usually the standard kind of significance test is just testing whether beta hat is equal to 0 or not equal to 0. So the null hypothesis is usually beta hat is equal to 0. Then of course this beta j, which is the true value, is equal to 0. And what we're left with for our test statistics is test statistic is beta hat j divided by the standard error of beta hat j, and that follows then a t distribution with n minus k degrees of freedom. Okay, so that's already useful, because now we can directly kind of derive hypothesis tests for OLS. We also can show additional kind of desirable properties of OLS, specifically based on the assumptions A1 through A6. So not even assuming normally distributed error terms, we can show that OLS has the minimum variance among all linear unbiased estimators. And this is kind of this famous theorem that suggests that OLS is blue, the best linear unbiased estimator. Okay. If we add this assumption of normally distributed error terms, we have an even stronger statement where, and this is called the Rao-Blackwell theorem, if A1 through A7 hold, then OLS has the minimum variance among all unbiased estimators. Okay, that's an even stronger kind of property if we add the normally distributed errors, but even with just A1 through A6, we have the famous Gauss-Markov theorem showing that OLS is blue. Okay. Of course, in the kind of sampling, for example, in the survey sampling context, this assumption of fixed X's or fixed independent or covariates is somewhat odd. And so it's important to kind of think about what kind of properties OLS has if we kind of relax this assumption of fixed X's, that X's are not random variables themselves. Okay, it turns out we can relax this assumption and of fixed X's and derive very similar properties regarding unbiasedness, consistency, and so on, based on stochastic X's. So now the X's are also considered random variables essentially. Okay. The assumptions are similar, but there are a couple of small differences, right? First, we again start with the basic linear model, and that is just the assumption that this linear model holds in the population, basically. Okay, and then instead of assuming that the X's are fixed, we're now assuming that the expectation of the error term conditional on the X's is equal to 0. Okay, so instead of assuming that the X's are fixed, we're now assuming that the error term, the expectation of the error term conditional on X is equal to 0. Okay, we're also assuming that basically kind of implicitly assumes that there's no correlation between the X's and the error term. Okay. We also assume that the X's and the and epsilon are independent and identically distributed. So this is not to say that X and epsilon are identically distributed, but rather kind of the combination. You could think of this as like the distribution of the combination of xn and epsilon n for one specific observation, like all those kind of sets of random variables are independent and identically distributed across observations. Okay. We have a few more kind of technical assumptions. I'm not going to go into the details of that. They're kind of like, for example, assuming that xn times epsilon n has a finite variance and things like that. But I'm not going to go through those technical details. There are a couple of more familiar ones. For example, the homoscedasticity assumption, stated here as the expectation of the square of the error term conditional on x is equal to just the error variance epsilon sigma square epsilon. Okay, and again the last assumption that the error term itself is normally distributed. Okay, so based on these sets of assumptions, they're a little bit more technical because we relaxed this assumption that the x's are fixed, but we can derive similar properties. OLS is still unbiased, and we can still derive a test statistic. The key point here is that the test statistic, this is basically if B1 through B7 holds, so we don't have to assume normally distributed errors, we can still derive a test statistic for our beta coefficient that looks quite similar to the t distribution that we derived previously, right? The key difference that you have to keep in mind here is that in the one case where we assumed non-stochastic axis, fixed axis, we had to assume that the errors are normally distributed. And based on this assumption that the errors are normally distributed, we were able to show that the sampling distribution of beta hat follows a t distribution, right? Keep in mind here that we don't have to invoke the central limit theorem, we don't need large samples. All we need is normally distributed errors, fixed axis, and then we have a sampling distribution for beta. So that kind of allows us to use OLS even in like very small samples where we can't invoke the central limit theorem. Here, with stochastic axis, we have to invoke the central limit theorem. So this test statistic and kind of the sampling distribution of beta, assuming stochastic axis, relies on the central limit theorem, so relies on asymptotic properties and large samples. Okay. If we and this, as you can see, this is a slightly different kind of way of writing this, but the test statistic ultimately, of course it doesn't follow a t distribution, it follows a normal distribution here now. But if you compare this sampling distribution beta hat following a normal distribution that is centered around beta with this given variance, this specification here is quite similar in the sense that we have here now the difference between beta hat and the true beta multiplied by the square root of n, and that follows a normal distribution with a mean 0 and this variance. Okay. The key point here is this is kind of the specification for or the basis for the Wald test, but it's essentially kind of similar in the sense that we're just looking at a scaled difference between beta hat and beta rather than just the sampling distribution of beta itself. Okay. Ultimately, we can derive kind of the similar test statistic, for a basic null hypothesis test for beta being equal to 0. That's again just the test statistic of beta divided by the standard error. The only difference is now that we're looking at a normal distribution with some, with mean 0 and some variance rather than the t distribution because we're invoking the central limit theorem. Okay. In addition, if we assume normally distributed errors, and we're going to talk about this in a little bit more detail as well, if we add this assumption of normal error terms, we can additionally show that OLS is the maximum likelihood estimator for beta. Okay, and that's another great property because maximum likelihood estimators in general have a couple of really useful properties themselves. And we're going to summarize those. So to summarize, we kind of started with this idea of kind of describing associations as conditional distributions. And I started this picture in one of the previous videos as conditional distributions without any clear assumptions about how the conditional distributions between different levels of axis differ. Okay, and what I mean by the conditional distribution is the probability distribution of y conditional on x, for x having a specific value. Okay, and now kind of summarizing, I know I went through this, slightly more technical, but ultimately what, the way you can think about this and visualize this is that we're making certain assumptions about the structure of the relationship between x and y. Specifically, we're assuming linearity. So now the way the conditional distribution of y conditional on x changes for different levels of x is now a linear function of x. Okay, so rather than going, up and down for different levels of x, like here, we now have a linear assumption about how the average level of y differs for different levels of x. Okay. In addition, we assume that we have constant variance, right? So the variance around our expected y for different levels of x is constant across levels of x. Okay, so these bell curves all have the same variance, the same standard deviation compared to here, right? And in addition, lastly, depending on whether we make that assumption or not, we can assume that we have normal error terms. So the shape of this distribution is not only with constant variance, but it follows a normal distribution as well. Okay, so those are all kind of assumptions that we can make about the underlying structure of the relationship between x and y. And of course, these assumptions may hold, but they may also break. They might fail, and we'll talk about how to diagnose whether these assumptions hold and what to do about those assumptions and what the consequences are of these assumptions breaking in the weeks to come. Okay. For now, all we can kind of summarize is that under these assumptions, or as I mentioned, particular subsets of them, sometimes we need normality as an assumption, sometimes we don't. The least squares coefficients are first linear functions of the data, and therefore have simple sampling distributions, right? Based on the fact that the OLS coefficient can just be described as a linear function of our x's and y's, the way we kind of derived it. It is an unbiased estimator of the population regression coefficients. We've shown that in the last semester. It is also the most efficient unbiased estimator of the population regression coefficient. So in other words, OLS is blue. This is kind of the result of the Gauss-Markov theorem, as we discussed. We can also show that it is that the least squares coefficients are the maximum likelihood estimators of the OLS coefficients or of the regression coefficients, and the least squares coefficients are normally distributed. Okay. After kind of showing these properties, one thing I want to briefly say or talk about is coefficient interpretation. And one thing that is mentioned in the Gell-Mann book and beyond is this important difference between interpreting coefficients as comparisons and interpreting coefficients as kind of effects, kind of giving them a causal interpretation, right? And what you have to keep in mind is that in general, the safest way to kind of interpret regression coefficients is to always think of them as comparisons and not think of them as like actual causal effects. In order to claim a causal effect of x affecting y, we need additional identifying assumptions, and we're going to talk about them towards the end of the semester, right? So in general, there are two different ways to think about this. On the one hand, we can kind of use this predictive interpretation, or as in the Gell-Mann book, kind of thinking about these as comparisons, where we interpret the coefficients as telling us how the outcome variable differs on average when comparing two groups of unit that differ by one unit in the relevant predictor while being identical in all other predictors, right? So this is just a comparison between units at different levels of x, okay? So this is comparing average outcomes, and it's talking about descriptive empirical associations. And whenever we have observational data, we should focus on that type of interpretation rather than the counterfactual interpretation. The counterfactual interpretation, or thinking about regression coefficients as true effects, interprets the coefficients as changes within individuals rather than comparisons between individuals, right? So here we would say the coefficient is the expected change in y caused by adding one unit to the relevant predictor while leaving all other predictors in the model unchanged. So here we're talking about relationships between variables, and this is kind of a causal structural relation, and we're actually talking about causal effects, right? And so the importance is to keep in mind that that we need more identifying assumptions in order to add this kind of counterfactual interpretation. And in general, especially when we work with observational data, we can only kind of think about interpreting regression coefficients from this predictive perspective, thinking about regression coefficients as comparisons. Okay. The last few things I want to talk about is quantifying uncertainties. So how do we kind of compute the standard error of beta hat? I kind of, when we talked a little bit about the properties of OLS under stochastic and non-stochastic axis, we already said that the sampling distribution of beta hat is centered around beta, so beta hat is unbiased, the OLS estimator is unbiased. But of course, it's important to know how far we can expect beta hat to deviate from beta on average. From a frequentist perspective, we're thinking about this as over repeated samples. How much does beta hat kind of vary between those repeated data generating processes, right? And I already showed you in the previous slide how the variance of that sampling distribution, again in the frequentist framework, the variance of beta hat can be written as sigma square epsilon, so that's the variance of the error term, times x prime x inverse, okay? And of course the standard error of that beta hat, or specific beta hat j, this is a vector of betas, this is one specific beta, is then of course the square root of that specific element in this covariance matrix, okay? Of course, we don't observe the variance of the error term because we don't actually observe the error. We only observe the residuals, so the actual difference between y and y hat. But we can use the residuals to estimate our sigma square epsilon, okay? And the way we can estimate our error variance based on the residuals is by taking the square of all the residuals, all the observed residuals, summing them all up and dividing by n minus k minus 1, okay? So dividing by the degrees of freedom, essentially, okay? Here, sigma hat epsilon is called the standard error of the regression. So that's basically the deviation from our predicted regression line on the average deviation from our y hat, from our predicted regression line, right? That's the standard error of the regression, okay? Based on that standard error, we can basically use the same techniques that we already talked about in the context of like hypothesis testing in general, right? We talked about how we can derive test statistics, specifically here, this kind of standard t statistic for the regression coefficient, where if we want to test a specific null hypothesis, usually that coefficient is equal to 0, we can divide the coefficient by the standard error, and that fraction that follows a t distribution with n minus k minus 1 degrees of freedom, okay? So that's the number of parameters minus, the number of observations minus the number of parameters. And here the minus 1 is added for basically for the constant if k doesn't count the constant but just the independent variables. As we talked about, the kind of most common null hypothesis is that the beta coefficient is 0 in the population, and when we talk about statistical significance, we say that the coefficient is significant if it is unlikely that we would have observed the OLS coefficient that we observed in our sample under the null hypothesis, if the null hypothesis was true, that the true beta is actually 0, okay? We talked about alternative hypothesis. We can kind of test one-sided tests or two-sided tests where the alternative hypothesis is that beta is larger than 0 versus beta is just not equal to 0. and the same kind of arguments regarding the rejection rule hold for a two-sided hypothesis test. We can kind of specify a critical value for that given t distribution, and if our beta hat divided by the standard error is larger, or the absolute value of that is larger than our critical value, then we reject our null hypothesis and we in favor of the alternative hypothesis. Okay. And we talked a lot about p-values. Of course, the p-value then gives us the probability under, assuming that the null hypothesis was true, how likely is it that we observe t statistics as high or higher than what we actually observed in our data. Or in other words, stated the other way around, given the observed value of the t statistic, what is the smallest significance level at which the null hypothesis would be rejected? Okay. A couple of notes, and we talked a lot about the problems with statistical significance, but I just wanted to kind of review kind of the basic frequentist perspective on OLS before we move on, because as you know from reading the book, the authors of our textbook are very critical of this standard conventional hypothesis testing framework, particularly in the context of linear regression. A couple of notes to emphasize. In this hypothesis testing framework, the possible outcomes of any hypothesis test are just rejecting or not rejecting the null hypothesis. It is never possible to accept a statistical hypothesis. Okay, we can only say, if we fail to reject a null hypothesis, all we can say is that the data are insufficient to reject the null hypothesis. Okay, and we talked about this in previous weeks as well, in general in the context of p-values. Another thing to note is that sometimes we're interested in whether two coefficients are different from each other. Right? It is important to keep in mind that testing whether two parameters are equal is basically equivalent of testing whether their difference is equal to 0. Okay. Then the important thing to note here is that, that testing whether the difference between two parameters is equal to 0 is not tested by overlapping or non-overlapping confidence intervals, right? Whether or not two confidence intervals overlap doesn't really tell you whether the difference between the two coefficients is statistically significantly different from 0 or not. Okay, maybe in the Q&A session we'll look at some examples. So you can have two regression coefficients where the confidence intervals are overlapping, but the difference between those two coefficients can still be significant. Okay. So speaking of confidence intervals, lastly, of course, we can compute confidence intervals for regression coefficients, just the same way we can compute confidence intervals for population, for sample means or differences in means and so on. And again, the confidence intervals describes a range of likely values for the population parameters beta. We can compute the 95% confidence interval of our beta hat by subtracting for a given critical value, usually for a normal distribution that's 1.96 for the 95% confidence interval. We multiply this critical value times the standard error of our beta hat, and we subtract and add it from our point estimate to compute the confidence interval. Okay, and we'll go through a practical example in the next video. Okay, and of course there's this kind of relationship or equivalence between hypothesis testing and checking whether the confidence interval includes a critical value or doesn't include a critical value. In general, if our null hypothesis is that the beta coefficient is equal to 0, what we're looking for is whether or not 0 is included in the confidence interval or not. If it's not included in the confidence interval, then we can reject the null hypothesis at that confidence level. But of course, we're not only interested in whether it's included or not, but usually we should also examine, like, what is the uncertainty around our estimate? How far is 0 actually from this interval? Okay. Again, we talked a lot about kind of the criticism of this standard approach. We'll talk more about this in the Q&A session. One important thing to keep in mind that we looked at by virtue of these simulations of the actual empirical coverage of confidence intervals is that the 95% of the confidence interval does not describe the probability that beta j is like the true coefficient, the true value is in this particular confidence interval, right? The 95% suggests the proportion of confidence interval that contain the true value under hypothetically repeated sampling, and that's what we showed in this example from last week. Okay. So this was a lot of material, a lot of review of kind of things that we talked about in the previous semester and in previous weeks, but I kind of wanted to provide a concise overview of kind of the frequentist perspective on OLS and make sure that we reviewed all that material before we move on to discussing the material in the book that kind of like goes beyond the classic conventional hypothesis testing framework. Okay. In the next video, I'm going to show you kind of all the concepts that we talked about in this video and the previous one in a practical coding example. I'm going to show you some basic regression inference from a frequentist perspective in R.